Good day, ECO235 students. We are still busy with topic 3, matrices. So we are continuing off from last week where we dealt with the basic concepts and the introduction to certain operations such as addition, for instance. So please ensure that you go through the basics and the operations before you continue with this week's work. Now, this week you'll be dealing with multiplications, so namely scalar multiplications and general matrix multiplications. And then you will be learning about 2 by 2 matrix inversion. And they will discuss the determinant, the inverse, and how it can be applied to solve economic problems. The prescribed readings is from chapter 6.3 to 6.5 of your prescribed textbook. And then the Jacques textbook is also very useful. That is chapter 7, section 7.1 and 7.2. Now let's begin with scalar multiplication. Now, scalar multiplication is essentially taking the product of a real number, so that is K, and a matrix A. So K is some real number and A represents some matrix, and scalar multiplication is taking the product of that. So then with the matrix A, you know that you have entries in that matrix. So this scalar K is going to be multiplied by every entry in that matrix. Now, following your laws of ordinary arithmetic, certain laws apply here to your matrices as well. The first one that we have here is the distributive law. So this is following on from ordinary arithmetic. So with your distributive law, you can take this factor A and you know that you can distribute it into these factors in the brackets. So then you can take A and it would be multiplied by B, and you can take A and separately apply it to C. So therefore you get A, C, right? So that is the distributive law. Now with matrices, if you have some matrix A and some matrix B, and you needed to get the sum of that, you could then apply your scalar to matrix A separately, and you can take the scalar K and separately apply it to matrix B, such that you have the product of the scalar K times matrix A plus your scalar K times matrix B. Then from your associative law, now the associative law says it doesn't matter how you group the numbers, the grouping or the association doesn't matter. So what you calculate first isn't going to affect the answer. So you know that you would typically deal with what is in the brackets first, so getting the product of BC, then have it times by A. But if the grouping was AB, for instance, and you first solve that, then multiply by C, the grouping or the association here doesn't make a difference in terms of the answer. So what you calculate first doesn't affect the answer. Now the associative law also applies to matrices. So here A represents some matrix and L is also some real number. So you could either solve this, then multiply it by some scalar K, or you could take your scalar K times L, so get that product first, then multiply that by your matrix A. So taking this scalar, and you would then scale up every entry in that matrix A. So here we have an example. So here you are told that you have two customers, customer 1 and customer 2, and goods are sold to them for April. And this table represents the sales of good 1, good 2, and good 3 for the month of April to these two customers. Now you are told that the sales for May of each good, these three goods, is 3 times the April sales. And then you are also told that the June sales of each good is 2 times the May sales. So how can we use matrices to determine the total sales of these 3 goods to these customers in May as well as June? So we're first going to express the original information we had for April sales, and we are going to express it as a matrix, and that is matrix A. So if we just go back, you will see that the goods for April sales for good 1, 2, and 3 for these 2 customers was 10, 12, and 14 respectively. And for customer 2, it was 15, 17, and 19. So how would I read this? Let's just take a random number. I could say, how much of good 2 would customer 1 purchase? And then I would find that customer 1, if I have a look in this row and I find the column for good 2, customer 1 would purchase 12 of good 2. And let's say I asked you, how much of good 3 would customer 2 purchase? So if I have a look, there's customer 2, and I read across the row, and I see, right, if I check this column, this is the column for good 3. So customer 2 would purchase 19 of good 3 in April. So this information is captured in this matrix over here. Now, remember, you are told that the sales for May is going to be 3 times that of April. So how do we express that? Well, you're going to end up getting a new matrix B. So matrix B is going to be the sales for May. And the sales for May was 3 times the sales of April. So K is that scalar 3, and it's 3 times the sales of April, and A was the matrix that represented the sales for April. So now what you do is you take this scalar 3 and you are going to multiply it by every entry in A. So as you can see, this was your matrix A. You are multiplying every entry in that matrix A by the scalar. So you're scaling this up by a factor of 3. And what you get is matrix B, which is your solution. And this tells you the sales for those 2 customers in May. So remember, the rows told you which customer it was. So customer 1 was row 1 and customer 2 was row 2. And the columns indicated the goods. So we had good 1, good 2, and good 3. So now I know, for instance, that customer 2 purchased 57 of good 3 in May. Or I could tell you that customer 1 purchased 30 units of good 1 in May. Now, finally, you are then told that the sales for June was 2 times that of May. So therefore, remember, by the associative law, it does not matter what the grouping is. So now you know that if you want to get the cells for June, we are going to call that matrix C. We know that that cell would be 2 times the cells of May. So if I say 3 times 2, I'm going to get 6. And I can then just multiply this factor of 6 to matrix A, which was your original matrix. And then you take the scalar 6 and you're going to multiply it by every entry in that matrix. And then you're going to get your cells for June. So now what I've done is I've grouped those 2, the factor K, which was 3, and then the factor L, which was 2. 2 was the factor for your June sales. It was 2 times that of May. I grouped those 2, and 3 times 2 gave you 6. And then I multiplied that by matrix A. Now, let's just check if we took our matrix B, which was your May sales, and each entry in this matrix B is multiplied by 2, which was the factor for your June sales. It was 2 times that of May sales. So if I take 2 and I multiply it by each entry in matrix B, which was your May sales, do I get matrix C? And let's check. 2 times 30 will give me 60. 2 times 36 is going to give me 72. 2 times 42 is going to give me 84, and so forth. So you can see that it yields the same answer. So whether you say 3 times A and obtain your matrix B and then multiply it by a scalar of 2, or if you say 3 times 2 and it yields 6 and then multiply that by your original matrix A, you will still get matrix C, which is your June sales. So with scalar multiplication that you just saw, a particular matrix was just multiplied by a real number, right? So each entry was then multiplied by that same real number. However, with matrix multiplication, you have two matrices that can be multiplied with each other. So if you have, let's say, matrix A and matrix B, those two can be multiplied such that you produce matrix C. So the product of AB can produce matrix C. But the only way in which that can occur is if matrix A has an order of M by S, so M rows by S columns, and matrix B has an order of S rows by N columns. So what do you notice? The columns of A in terms of a number matches the rows of B. So columns, rows of those two respective matrices are the same. So therefore matrix C, which is given by the product of A and B, will have an order of M by N, which is the outer numbers. So once you determine the order, you will then be able to figure out what would be the new order of your matrix C. So in terms of matrix multiplication, these are the following laws that can apply. So provided your matrices A, B, and C have the correct orders for sums and products, so doing your additions and multiplications, then these laws would apply. So again, you have your distributive law. Now notice I'm not using lowercase letters, but uppercase letters to reflect that these are matrices. So you could distribute or apply A separately to B and C to get the product of AB plus the product of AC. And this still applies by virtue of the distributive law. And then with the associative law, does not matter if you get the product of BC, then multiply by A, or get the product of matrices AB, then multiply by matrix C. You would still yield the same answer. However, there is an exception. The commutative law does not apply. So where it does apply in ordinary arithmetic, if you say, let's have a simple example, AB, let's call A 3 and B is 2. 3 times 2 gives you 6, right? Or I could say 2 times 3. It also yields 6. However, with matrices, the product of AB is not going to be equal to the product of two matrices B, A, right? So saying matrix A times matrix B is not going to give you the same answer as saying matrix B times matrix A. There are some exceptional cases, right, where the commutative law would apply, but those are just exceptions to the rule. And just in terms of the commutative law, if you commute, if you travel, you are going back and forth from one location to the other. So it says that it doesn't matter if we swap the numbers, we'd get the same answer as you saw as I did over here, but it does not apply in this case. Right, so here's an example. I will continue the next part of the slides with this example.